Hi, everybody, and welcome to the History of Networking at the Network Collective. We keep changing the name every podcast.
That's the name. The History of Networking at Network Collective. That's it. That is the name.
That's the name. History of Networking. So there you go. So today we have Daniel Walton with us. I worked with Daniel way back at Cisco. Boy, Daniel, that was a long time ago. I remember when I pinged you and I asked you about this. Your wife, Allie, PM'd me and said, "Is Daniel really old enough to participate?"
That sounds like Allie, that's for sure.
I'm now old enough to be part of history, I guess. That's beats the alternative.
Very true.
So tell us about yourself, Daniel. Where are you working now? What you working on?
So my name's Daniel Walton. I work at Cumulus Networks. So I'm a principal engineer at Cumulus. What do I work on? So that's a good question. So historically, I've worked on BGP for a good chunk of my career. At Cumulus, I get to work on lots of different stuff. I still work on routing and BGP, but just not exclusively anymore. I guess lately I've been working on this thing called NCLU, which is sort of our CLI for Cumulus. So that was sort of a big project last year.
That's very sad.
That it's a big project?
No, that you're doing a CLI.
That was fun. Yeah, I got to do something different. In
Python.
In Python, yeah. I'm a big Python fan.
So you wrote your BGP in Python, right?
I have done that. I sort of did it as an experiment once. It ended up not really going anywhere, but it was kind of cool. It was. Cool. I had a SQLite database because I started thinking, I was like, why has no one ever done BGP with a SQL database? So I did Python with a SQL database for BGP.
Oh, wow, that's cool.
Nice.
So Donald, been a long time since I've talked to you. This morning, twice, free range routing call.
Yeah, I'm Donald Sharp. I actually also work at Cumulus Networks with Daniel. He sits across the road from me. Yeah, and he throws stuff at me too. I ostensibly work on routing, and I help herd the free range routing cats.
Cool. All right, Jordan.
So yeah, I'm Jordan Martin. I'm one of the co-founders of Network Collective, and I do not work at Cumulus. Never have, nor Cisco. So no,
well,
I work
we're just gonna have to kick you off the call.
I know. I feel very much an outsider in this call right now. No, I work as a principal consultant for data center technologies at Core BTS.
Cool, excellent. All right, so today we are talking about the history of BGP optimizations. You know, as much as everybody likes to talk about how slow BGP converges, it actually converged more slowly in the past. At least until Daniel got his hands on it and started playing with it. So I remember this all started, I think, in the scaling team, right, Daniel, at Cisco, when we were like all the DNA team and all those people were like wandering around together doing stuff.
Yeah. So not my first job, but one of my first jobs at Cisco was on this routing protocols, scaling, and deployment team. So we got to work with lots of different customers on helping them with BGP configs and design and things like that. And then sort of the other half of the job was trying to figure out where all the bottlenecks were in BGP and trying to figure out how to fix them. So a lot of stuff sort of happened in that time frame, or I guess a few years after that. I eventually left that team and went into development. So I was a BGP developer for iOS for about 6 or 7 years. So sort of, most of this is like 2000 to 2006-ish sort of time frame.
Yeah, that's cool. I'm trying to remember when I left Cisco. It was after you did, I'm pretty sure, because I think you went to Cumulus before that.
Yeah, I left
in something like
2013.
That. Yeah, something like, I don't know. Okay, I don't know when it was, but yeah, that's cool. So, all right, so tell us about what happened? Like, let's just go down the list. I see there was a lot of stuff. You sent me a nice, cool document that we can talk about. But
yeah, so I started trying to jog my memory and was writing stuff down. So the first thing I could think of was actually before I was involved with BGP, and that was peer groups. So initially in BGP, you would configure all of your neighbors, and BGP would go through and it would build all the updates for the first neighbor, and then it would build the updates for the second neighbor. And it would basically do them all individually. And this didn't scale very well. And then you had this other problem of, well, your config became really, really big when you had lots and lots of neighbors. So someone came up with the idea of doing peer groups, which is basically like sort of like a little template, right? So you have a peer group maybe it's called ISP. And you say, okay, this peer group ISP has the following, configuration, and then you can assign peers to that peer group.
And this relates back to TCP, right? And the way BGP interacts with TCP, from what I remember. I'm trying to remember, like, when you were working on this, there was this thing about building TCP segments for BGP and having to build an individual segment for every peer that you were talking to. And doing something like this actually helps you in the optimization in that direction someplace. I'm trying to.
So the big scale benefit with peer groups is so let's say I've got 10 neighbors that are part of a peer group. You can build the update for the first member of the peer group and then basically just replicate it for the other 9. So it just saves you a lot of CPU in terms of how many cycles it takes you to put together all these updates.
You're not actually doing a mem copy. You're just pointing to the same update to multiple neighbors until you've pulled the entire peer group out, and then you can actually take the packet that you've built in memory out. And by the way, as a matter of reference, do you remember how many peers and how many routes before you started playing with this?
I remember it was really bad.
Old how many script. Yeah. I was just trying to remember exactly what it was, because before and after would be really interesting to try to remember.
I should have looked that up. I probably could find the slide somewhere. I don't remember the numbers. I remember that the graph, like after we started working on it, just like, had a nice little curve up. So that was pretty cool. But yeah, initially the how many peers, how many routes thing was, I wrote this test that it measured, what was it? Given a certain number of routes, how many peers could you converge within 10 minutes? And so this was like initial boot up or, clear IP BGP star convergence is what we were measuring. I remember like one customer said, well, I want to know what the answer is for 5 minutes. And someone said, I want to know what the answer is for 15 minutes. So I sort of just picked in the middle and picked 10. And I remember I told that story at Networkers one time, and someone pointed it out. It's like, well, you didn't make either customer happy,
Daniel runs the ATM of BGP peering test.
Yeah. But yeah, that was a big sort of measuring stick that we used for several years to sort of gauge like how our scalability was doing. And it did increase pretty dramatically over the years.
Yeah, I remember it increasing. I just don't remember how much. I know it was like maybe even a 10-fold increase or something, or even more.
Oh yeah, at least.
But I don't remember exactly what the numbers
So,
were.
I mean, I guess one thing that we should be careful. I mean, we should remind people of this is the mid-90s, right? So CPUs were not exactly known for their blazing speed at that point in time, especially CPUs chosen by vendors to put on their routers or switches.
Right.
They were not necessarily bleeding edge.
Yeah, I think the hottest box we had in the lab was the 4500 or 7200 VXR, and that was even after these tests. So, like, I think you were testing on like a 7500, right? Yeah,
we had a lot of 7500s and 7200s. So yeah, not a whole lot of CPU. Memory was the other big thing, and this comes up like several scalability things we tried to fix. We were just so limited on the amount of memory that these boxes had. Because like I remember a lot of the 7500s only had 128 megs, and these were service providers that were running them, so they had the full internet table on them. So there were a lot of times where it's like we couldn't do a feature because it would, we'd basically run them out of memory as soon if they upgraded and had this feature enabled.
128 meg with like 325,000 routes or something like that around that time.
Back then, it was probably, I think it was like 120 or so. It was around 1999 or so. It was around 100,000. give or take. But yeah, it was a pretty significant, limitation that we had to work around. Now it's like you don't really have to think about it that much. It's like got plenty of RAM.
That's because folks like Jordan buy all the memory they want to.
Somehow I'm on the receiving end of this. I don't buy it. My company sells it.
Okay. Oh, Jordan's company goes out and sells as
Yes.
much memory as they can sell.
Absolutely.
There you go.
And you need all of it, all of the memory.
But yeah, the peer groups thing that was pretty early on and was pretty significant. And I remember like when I first started working with BGP, they had this limitation. It's like, well, you had peer groups, but all of the members of the peer groups had to be on the same subnet. And that was like a really early restriction. And that was because they couldn't change the next hop. Like you had this update and you had to send the exact same update to all of the neighbors. So even the next hop had to be the same. And then I guess eventually enough people yelled and screamed that said, this is unrealistic trying to use this, that they changed it so they'll rewrite the next hop at the last minute. So then peer groups got much more popular. But like if you go back and read, like the book to read in the 90s to learn BGP was the Internet Routing Architectures by Sam Halabi.
Yeah, Halabi.
And in the book, it has that limitation. It's like if you do peer groups, they have to be on the same subnet. So that was where I guess I probably first heard about that was that book.
Wow, that's really cool. In fact, I think that was the first book published by Cisco Press.
Really? I didn't know that.
I think that was the first book published by Cisco Press.
I think he eventually did a second edition, but...
Yes, he did a second edition. Yeah, Sam eventually did a second edition. He's disappeared off the face of the earth now. I'm thinking that Inca or Srihari might have done the initial peer group stuff, but I want to say it was Inca. But anyway, who knows? It's lost in the mist of history.
You should have them on.
Yeah, well... So you said peer groups went in the mid 90s. That made a big difference. So after that, you still saw this. The performance still wasn't that great, right? I mean,
yeah, it was still. So I guess I really got involved with it. I guess starting around 2000 when I was on this deployment and scale team, and we had by that point the internet table had started growing enough. We had a lot of customers that were hitting scale issues, like I remember SprintLink. I did a lot of work with SprintLink, and so they had boxes that had, 120 neighbors, which you had 100,000 routes. Trying to converge them over 120 neighbors, it could take a while. So one of the, I guess, first things I was involved with was read-only mode. So read-only mode in BGP is this sort of phase when BGP first starts up. It just sort of sits there and is really quiet, and it just sort of accepts routes from all of its neighbors. And then after it has all the routes from all the neighbors, it says, okay, now I'm going to figure out which one is the best path and put them in the routing table and start advertising them and that whole thing. So read-only mode came about. So we were doing some work on the GSR platform at Cisco. And GSRs, it was this distributed architecture where you had an RP and had all these line cards. So the GSR had to sync, the forwarding table down with all the line cards. And it did this. I remember the messages were called XDR messages. And I can't not remember what XDR stood for, but I remember that that's what it was. And so what would happen was you would boot the box and the first BGP neighbor would come up and we'd learn the full internet table and we'd install them in the routing table and start building XDR messages to send them to the line cards. And then 2 seconds later, the second BGP peer would come up and we would learn the full internet table again. And that would trigger, best path changes and changes to the routing table and whatnot. And would cause more XDR messages. And so this just kept kind of happening. Like if you've got a box with 100 neighbors, you would just get all this crazy churn at the beginning. And eventually the box would basically run itself out of memory, building all these XDR messages, trying to get the line cards converged. And so I was working on this with, there was an engineer, I think she's back at Cisco now. Her name's Gargi Nalawad.
Yeah, that's right.
Anyway, Gargi and I were working on this, and like the box just keeps running out of memory. And we like look at each other and we're like, we just need BGP to shut up for a minute, and let the peers come up. And so that's sort of how
we've all said that from time to time.
Exactly.
I say that to Russ all the time.
Yeah, we want BGP to shut up for a minute.
Yeah, so read-only mode was started as a way to get GSR to converge on a reboot, just without falling over and dying when these neighbors would come up in this cascade, basically.
I'm trying to remember. I think the GSR was different because the GSR was, so the 7500 effectively had this backplane that was basically the AGS Plus, which was, instead of being cabled, it was just a pluggable architecture. Like it was basically an AGS Plus with a pluggable architecture, and then with like a circuit board in the back instead of cables. And I think that the GSR is the first one where Cisco actually designed a real backplane, like a crossbar fabric or something like that. So it wasn't like just an Ethernet port or something on the card. It was like actually something different. So it had its own QoS and everything. It was like the first time that it had been done. So it had all this weird inter-process communication going on that no other routers seemed to have at that time.
Yeah, you had to get, each line card had a full copy of the fib. So it was, you had to get all of that state down to the line cards, as quickly as you could. In hindsight, I don't know why we just didn't tell the Ceph guys to fix the line card download so that they didn't run the box out of memory with these XDR messages, but I don't know. I guess we got to it first or something.
Well,
but it's still like, read-only mode it's still used a lot. Like we use it. So Donald and I work on FRR. So we've got it in FRR just, to help with convergence at boot up. So it makes a pretty big difference.
Now, when you come out of read-only mode, didn't you do something to bring it out of read-only mode, or was that just?
Oh yeah, so we had it. So what we would do is once all of the neighbors came up, we would wait for them to send us all of their routes, and then they would send an end of rib marker, right? So it's like this special little update that they can send you to say basically, hey, I'm done. So once we received an end of rib from everybody, we would exit read-only mode. There were some other ways to exit too. Like there was like a 2-minute timer. So at most you would wait 2 minutes. If you had, a neighbor that was just misconfigured that would never ever come up, we had to put some smarts in to not wait on those neighbors, because we didn't do that initially. And we quickly found out that almost everybody has at least one misconfigured neighbor somewhere that is never going to come up. And so all the boxes would always wait the full 2 minutes. So we
actually putting smarts in BGP.
Yeah. BGP's awesome. What are you talking about?
So is this kind of the genesis for other routing protocols for their read-only modes, or?
Does EIGRP have such a thing?
Well,
yeah.
It does, and that's exactly why I was asking the question. Actually,
I don't know. Where did you guys get the idea to do it for EIGRP?
So basically, Donnie always just went through the BGP code and figured out what he could grab from the BGP code.
I don't think you could actually claim he actually ever looked at the BGP code. But I probably shouldn't speak for him there. But
I did not know that EIGRP had done that also.
Yeah, it's got to read only mode.
So actually, OSPF and ISIS do as well now, too. There are ways you can exchange a hash. Like in ISIS, of course, you have a database descriptor, so it's always had descriptor, so it's always been that way. But OSPF also now has a read-only mode where you can send an end of rib marker and say, yeah, I'm done. Now you can run SPF or whatever after first convergence. So, yeah, I think that was all stolen from you, Daniel. I think you should be paid a lot more than you're paid.
Get a royalty or something.
I'll bring a jelly bean by a little later today.
Nice.
So read-only mode's really cool. And then after that, I remember that, it was creeping up, but a lot of people, particularly SprintLink, this was Peter Lothberg, right? At SprintLink, mostly. Who still gives me a hard time every time I see him about BGP convergence. Anyway, we're still complaining about BGP convergence. So you did, after that was update groups, right?
Yeah, so update groups came about. So I guess I'll explain what update groups are quickly first. So an update group is just you take all the neighbors that have the same outbound policy and you stick them in a group much like a peer group, where you just build the updates for the first one and then replicate the updates for all the members of the update group. And this came about, I mean, we had peer groups, and if a customer configured peer groups, they were set because they got all of this great update replication, you know, where you do the work once and then you just copy them for all the other members of the peer group. But we had a lot of customers that just didn't configure them. And if they didn't configure them and never called us, that was fine. But they tended to not configure them, and then they would call and complain about slow convergence. So sort of our workaround is, instead of like trying to educate, you know, this huge BGP deployment base that we had on peer groups, was it's like, all right, why don't we just do this dynamically? So Gargi implemented this. I remember she implemented it, and this was right when I had joined the iOS BGP team. So this was the very first thing I ever code reviewed. I remember. But yeah, this was pretty, you know, pretty popular. Made a really big difference. It just saved everybody a lot of configuration, you know, work. It's like they got all the benefits of peer groups in terms of scale, but they didn't have to actually sit down and configure them if they didn't want to. We still tried to get people to use peer groups just because it made the configs smaller and easier to manage and troubleshoot. But it was no longer, you know, a must-have in terms of scale.
The peer group is actually, manually configuring it is actually more efficient at figuring out what should have the same updates than the update group ever could, right?
Well, no, the end result ends up being the same. Because even like with update groups, if you configure peer groups, it basically just still goes through all the neighbors and looks to find all of the ones that have the same outbound policy. Okay. And I was thinking about this when I was writing, you know, the notes for this thing was, even if everybody had always configured peer groups, we would have eventually done update groups anyway, just because you had all these things added to BGP so like add path, for example. Add path is this thing you negotiate in the BGP open capability. And whether or not a neighbor negotiates add path has an impact on what updates you send them and the formats for those updates. So there are all these things that come up that have a role in update group selection that you don't know about until the neighbor comes up. So we would have had to do them eventually anyway, even if, you know, everybody had been diligent and configured them.
Oh, cool. Great. All right. So that probably increased the performance some, because actually it just brought peer groups to everybody, right?
Yeah, yeah.
And then after that, I see on your list here update packing.
Yeah, so update packing. So this is really where the I guess the curve on that old slide really started to take off in terms of the performance. So update packing is just in BGP you have an update, and at the top of the update you have a list of attributes, and then after that you have all of the prefixes that share those attributes. So let's say if your entire BGP table, you know, if all of the prefixes only use 10 different unique sets of attributes, well, ideally you could advertise the whole table in 10 updates. So let's say you've got 10,000 routes, right? 10 updates, boom, you're done. So that's what you would call, you know, 100% packing efficiency. The inverse of that would be 0% packing efficiency, where you send one prefix in every update. So when I got involved with this and we were looking at it, I forget what the exact number was, but we were something like, you know, 20% packing efficiency or something really, really bad. Like we were not putting very many prefixes in each update. And we would end up building multiple updates that all had the same set of attributes, and each one would have 2 or 3 prefixes listed in it. So this had, you know, pretty negative impact on scale. So the piece that I worked on was I wrote a bunch of code that indexed the BGP table by attribute set. So I could say, given this attribute set, you know, go and visit all of the different prefixes that use that attribute. So
in memory, what a lot of people don't understand about the way BGP works is in memory, the BGP table is not held as a BGP table. Like there's not a route with its attributes. There's actually an attribute table and then there's a route table, right? And then the BGP attribute table actually has a set of pointers, or the routes have pointers to the attributes that they use. And so it's actually not one unified table. So many times we talk about a BGP update going all the way through the network. There's no such thing as a BGP update that goes all the way through the network. It's actually peer-to-peer.
Yep.
And it's ripped apart into multiple tables and then rebuilt at every hop. There's no update.
Yeah, you end up internally you end up like sort of pulling the attributes out and sort of storing them off in a different table, and that's just a way to save memory, which was such a precious commodity. I guess we had to do things like that to not run out. But yeah, the update packing thing. This was one of those ones where, if we had plenty of memory, we would have just said, okay, go walk the table, the whole BGP table, build all the updates you need all at once, put all the prefixes in, and then just send them all at the end, and you would be done. And I remembered I did try doing that, and the box just fell over and died because it ran out of memory 2 seconds into this process or whatever. So this is again like the 7500s that had 128 megs. It was just a real limitation that we had to work around. So that was why we had to do the whole piece of, walking the table, indexing the table based on attribute, was so that we could build these updates and pack them efficiently without running the box out of memory. So remember we did this, and this gave us a pretty huge jump in terms of BGP scale, right? Just in terms of how many peers we could converge and how fast and things like that.
Yeah, this also impacts TCP again, because each BGP segment that you send has to be pushed as a BGP segment or TCP segment or whatever, right?
Yeah.
So that's like your windowing. You're actually waiting for an ACK, all of this other stuff. It impacts your window size. The more you can pack in a single BGP update, the faster TCP, the larger the segments that TCP is sending, and it makes the TCP windowing a lot more efficient. Yeah,
you end up if you're packing efficiently, you're sending less data, right? So there's fewer ACKs that have to come back and you have to process. This actually reminds me, I didn't have this in my list, but another thing that we worked on around the same time frame was so the TCP ACKs were a problem actually. So eventually we got to the point where we could build all these updates very, very quickly and efficiently, and we would send them out. And then we would just get this massive wave of TCP ACKs that would come back to the box at one time. And, these are all destined for the RP. So I remember all of those packets, like on a GSR, you've got these distributed platforms or whatever. All these packets ended up going into these interface input queues. And we had problems where the input queue would fill up with nothing but TCP ACKs. And so at that point, we were start dropping TCP ACKs, which was just pretty horrendous, because then you've got to retransmit and whatnot. It was really kind of bad, because you'd done all the work to get the data there, and he'd ACKed it, and then you drop the ACK. So we ended up doing, I think we increased the input queue size. There was also this thing called selective packet discard that iOS had.
Yeah, selective ACK, yeah. Mm-hmm.
And this was like a separate input queue for routing protocols traffic. So we ended up getting BGP basically so that the TCP ACKs could go on the selective packet discard queue, which was deeper. So that made a difference. What else? I remember this queue was like 70 packets deep or something. And I was given a scale talk one time, and I was basically complaining about this. I was like, who in the world set this queue to only 70 packets deep? And at the time, my VP of iOS or whatever, Joel Byan, was in the room. And he stopped me. He raised his hand. He's like, actually, I'm the one that set that to 70 packets. So that was a little awkward. To his credit, he's like, I think I just picked a number out of thin air. It's like he didn't have any scientific reason for why it was 70.
Well, right. But I mean, in the level of efficiency you had when you picked that number as well, I'm sure that queue was perfectly fine, right?
Probably plenty deep, you know.
Right. You were fighting your own efficiency then. All of a sudden you're getting back more information faster.
Yeah.
Was this classic iOS, Daniel, I assume?
Yeah. This is iOS.
So classic iOS has this thing where when you create your own socket, you can control the queue size yourself and tell the underlying infrastructure how many packets you expect it to receive. And that was one of
Would that trickle down to the interface input queues, or?
I don't know. I'm thinking about that.
Yeah.
I ran into the same kind of problems. Not to digress, but I ran into the exact same kind of problems with EIGRP, where you would get all of a sudden more packets than you could handle, the input queue can handle, and you'd end up dropping, and then the whole world just kind of fell apart.
Yeah.
But which is, but.
Yeah, and wasn't there something, Daniel, where you went into TCP and actually did a push? Like you told TCP when to send a segment?
Yeah,
I think that was coded someplace in there.
There were some things you could basically queue up a bunch of data and then say, okay, I'm ready. Now go send it. I forget what that was. It's like the push flag.
Well, the problem
or
is if you don't fill up a full segment, TCP was actually waiting for the full segment to get full before it would send, or there was some timer, right? And so then you could have BGP could actually say, no, I'm done.
Yeah,
okay,
you could tickle TCP and tell it that you were finished more or less, and go ahead and send what you have.
Yeah.
Another thing we did with TCP was the whole the path MTU discovery and max segment size and that whole thing. I forget the details. Like the default max segment size was like 536 bytes or something for some weird reason.
Right.
And I remember we bumped that up to like 1460. Since they're from 1500 on Ethernet, and that was another one we did that made a big difference in fewer TCP ACKs and all that stuff. I don't remember if we ever turned on path MTU discovery by default.
I don't remember either.
I'd have to go back and look.
Yeah, cool. So you got to 100% packing efficiency effectively before it was over with.
Yeah. So by the end of that, we did the update packing. We fixed the input queues. We fixed the max segment size, and like the scale numbers were like through the roof compared to what they had been, 3 or 4 years before that. So I don't remember the exact numbers, but they were way, way, way higher. So yeah, it was a big improvement over several years. But after that, I mean, I think we kind of got ahead of the curve for a little while. Like we stopped hearing complaints about slow, scale problems and convergence and whatnot.
Well, then the problem moved to convergence itself, right?
Yeah. So single route convergence, right?
Yeah, single route convergence instead of initial.
Yeah. So single route convergence in BGP is kind of a different beast from your initial clear IP BGP star convergence. So single route convergence, it's like I've got one route that flaps somewhere, and it takes however long for that to propagate, across the internet. And this is where, to me, when people say BGP is slow, I kind of think this is what they're talking about a lot of times, is like how long it takes something to converge, worldwide or internet-wide. And a big part of this comes down to this. There's this timer in BGP called the min route advertisement interval. And this is, in the original RFC, they had this statement that said something like, you should never advertise a route to a neighbor more often than once every 30 seconds, right? So if Russ and I are peers, I shouldn't advertise 10.0/8 to him, every 2 seconds. There should be this 30-second gap in between advertisements. What they didn't consider, and this is before my time, so I don't really know what all went into it, but they didn't think about like how much memory that would take to keep track of when did I send each prefix to each neighbor. It's like you would basically need a timer, for each prefix, in each neighbor. And nobody ever implemented that. So instead, what everybody implemented was just a timer for when was the last time I sent an update to a neighbor. So they had one timer per neighbor. And so what you would see is BGP would send out, a wave of updates to a neighbor. And then for the next 30 seconds, it was basically just anything that happened for the next 30 seconds had to queue up and wait for this min route advertisement interval to pop. So this really, really slowed down convergence a good bit. I went back and looked. So the original RFC called for 30 seconds basically for all neighbors. I remember iOS did 30 seconds for eBGP and 5 seconds for iBGP. At some point, I got really frustrated, and I just sort of snuck in a bug fix that dropped it to 0 for iBGP and 5 seconds for eBGP. So yeah, I didn't. I remember I ran our test, and they all passed, and we just kind of rolled the dice and did it. But we never got any complaints, so it worked out.
Well, reducing to 0 or reducing to 5 actually does increase the number of updates that are transmitted, right?
Because, yeah, it can. So BGP, like if you put 4 routers in a mesh, right, in BGP, and you have a loopback on one of them that you're advertising, and let's say you shut down that loopback. So BGP has to send a couple of different cycles of messages back and forth before they figure out that none of them have a route to that loopback anymore.
Yeah, it's the classic hunt.
Yeah, path hunting.
Path hunting, the shortest to the longest AS path, basically.
Yep. So it does increase, I guess, the number of messages that are exchanged in path hunting some, just because you're reacting so much faster. Yeah. But you're at the trade-off of basically sub-second convergence. So like in FRR, I set this timer to 0 for both eBGP and iBGP, and BGP for a single route change is sub-second, right? I mean, it's very, very fast. So if you change this to 0,
it's still too slow though, Daniel.
Then sub-second's too slow.
Because it's BGP, it's still too slow. I mean, that's just.
Yeah. So yeah, I mean, if you change this one timer, it makes a huge difference. I kind of regret that I didn't make it 0 for eBGP also. The only reason I didn't at the time was dampening was still pretty popular, and we're kind of worried that it's like, all right, if we set this to 0, then people may start magically being dampened by their providers because we'd be sending out updates at a much faster frequency.
Yeah. Well, dampening is still a thing sometimes. People still do dampening sometimes, so you can't ever tell, right? Yeah. It's kind of it goes in and out from sometimes, right? So popularity.
It's that's another one that sort of slows down convergence worldwide, right? It's like if things start getting dampened, that has a pretty big impact
on convergence speed.
Yeah.
Sure. And the right place. Yeah, and the right place to do dampening really is on the interface towards the peer, on the peer itself, not on the route, but
Yeah, you shouldn't be dampening like your service provider, right? You should be, if you're the service provider, you dampen, the mom and pop ISP or the customer or whatever.
Right. So starting in the mid 1990s to the mid 2000s, thereabouts, right? Is that when MRAI was done? The work on MRAI was done.
So I made that change. That was probably, let me think. That was probably like 2004-ish. And I did that only in iOS. I don't remember. I worked on iOS XR and BGP for a little while, but I don't remember what their timers were. My guess is probably something reasonably
I think
low.
everybody sets them 5 and 0 now by default or something like that. Or even 0 or 2 and 0 or something like that, pretty much. Yeah. So we're talking about a 10-year journey in getting from the point where, and along this time, of course, the memory size was going up, the processor speed was going up. Donald, do you remember when the first x86 processor went into a Cisco router? I don't remember.
No, I don't remember.
When Cisco switched from RISC to x86.
Probably the mid-2000s then.
Yeah, probably about the mid-2000s. So, we're talking about a performance journey from the mid-1990s to the mid-2000s. That's actually pretty amazing that all this work went across a 10-year period. A lot of times when people look at these protocols today and the performance they have and stuff, they think, that was probably done in a couple of months. But, I mean, this is 10 years of work to get to the point where the performance was reasonable enough to be usable.
Yeah, it took a while. I remember too, like you would just you'd find one bottleneck and you'd work through that, then you'd find the next one, right? And you just kind of had to keep chugging along until eventually you got to this point. It's like, okay, this actually is very fast now, and scales very well.
Yeah.
So it did take a while.
And all those lessons have been poured into free range routing.
A lot of them.
You say that, right? But I think we had an argument recently about MRAI and what the value should be.
Yeah. Oh, it's a continuous, ongoing thing, right? With MRAI, particularly in the data center space, where it should be 0 always, versus acting as a route server in an IX fabric, where people might actually be dampening you, and you don't know, right? So you can't necessarily throw a lot of messages at them and assume that it's just going to work. Yeah. So
it's been interesting, like working on FR. It's like you see a lot of the same problems, or I've seen a lot of the same problems and scale issues or bugs or whatnot that I saw in iOS way back when. So it's been kind of cool. It's like, I remember fixing this or what we did. Like update groups, like when I got to Cumulus, I guess about 4 years ago. Actually, when I got to Cumulus, peer groups didn't even do update replication. Like we put that in, and then we put in update groups, and we've done lots of scale fixes. So it's been pretty cool. Like you get to solve a lot of the same problems again.
Yeah, it's really cool.
Hopefully in a better way.
All right. Well, it's been great. I mean, do you have any more questions, Jordan? Any?
I actually have this rather in my head. So we talked a lot about how, we were constrained on processor and memory, and that seems to be kind of a solved problem now, at least for the most part. What are we fighting a similar problem now? Is there something that we're fighting against like we were then with modern topologies? I'm just kind of curious, talking to three very experienced engineers here about building routing protocols.
So the first thing that actually comes to mind is that the decisions and algorithms chosen for low memory and low speed CPUs are not necessarily the same algorithms that you're going to choose for high speed, lots of memory. And those decisions guided the architecture of how things were laid out. And it's not always easy going from A to B to take advantage of the new memory and the new CPU power.
Yeah.
Makes sense.
Yeah, like dampening. Dampening was absolutely a way to, like they didn't want one misbehaving thing to kill the CPU of every router on the internet, right? So that's how dampening got going. Like that. I mean, now I wonder how many routes you would have to have dampened to or flapping to significantly, raise the CPU on a modern box.
Do you remember those presentations at Nanog about the percentage of routes that flapped all the time? And there were like discussions around if you set dampening to this, it would drop what percentage of those routes and stuff. It was pretty interesting that.
I remember RIPE had this set of parameters that they published as guidelines, right? So RIPE had these guidelines of like, you set the dampening half-life to this and decay to this and whatnot and whatnot and whatnot. And this was like the de facto thing that folks were supposed to follow. And I forget, I started looking at this for a customer or something, and I found out that the guidelines that they published wouldn't actually dampen any routes. Like there was this thing where your penalty had to go above a certain amount. But with the numbers that they had that they recommended, the penalty could never go above that number. It could equal it, but you didn't dampen if it was equal. It had to go above. So I remember that was kind of funny. It's like, yeah, dampening is not really doing anything if you're following the recommended guideline. They changed it. They changed it pretty quickly there after that.
So Jordan, I think your question is a valid one in that this is one thing. Donald's answer is one answer that's very important. Is that we're dealing with protocols that were designed on much smaller processors and designed for a different world. And so, we're dealing with this. Well, maybe somebody does have a processor out there that's still that slow, right? And
right.
so
we see older gear, so we can't just assume that everyone's operating it. Yeah.
So what do you do about that? And today, I think we're starting to see more problems around, when we talk about OSPF and ISIS later on in different video casts, maybe we can talk about a little bit about microloops. And in reality, microloops are, and the next one we're going to do with Daniel is talking about churn. And in reality, these things are impact of having enough processor that hysteresis states were states in the protocol that would never have been observed in a very slow processor. Once you do dampening and all this other stuff, the convergence is just so slow that you don't even recognize these things exist because they don't occur in the wild. But when you get a fast enough processor and enough free memory, all of a sudden your speed goes up enough that you start seeing weird problems creep in the design of the protocol itself that you never would have guessed were there.
The other thing that I think might be worthwhile pointing out is pretty much all the performance issues I've ever fixed have been a poor choice of algorithm more than anything else. And that's the correct algorithm and the correct data structure chosen for whatever problem you're doing. This isn't necessarily a networking issue. It's a programming issue where people choose the wrong data structure or the wrong algorithm, and it kills your performance. And that's what you really need to look for. Like
using SQLite with Python for BGP.
Sorry, you didn't say it.
I got it to scale to data center type numbers. You wouldn't want to throw a full internet table at it, but it worked. Like I said, it was a science project.
That's cool. So anything else, Jordan? Anything else, Donald?
No, I'm good.
All right. You don't have a blog or anything, do you, Daniel?
Not networking related, no.
Oh, well. See,
are you on any social media anywhere where people can find you?
Yeah, I'm on Twitter. I'm dwalton76 on Twitter.
Okay.
So not terribly active, but yeah, you can follow me. Maybe I'll tweet something.
All right. Well, all right. Excellent. Great. Well, thanks, Daniel, for coming on. And
yes, thank you.
Thanks for having me.
Yeah.
Thank you guys for doing this. Like when Russ was telling me about this, I was like, that's a really cool idea because like some of the things that Fred Baker mentioned, I had never heard. Right. So I think it's good to get some of this stuff down.
Yeah. Oh, yeah. Yeah. I think so, too. Yeah. And we'll have you back on to talk about churn because that's an interesting little piece of history as well in AdPaths, how that came about. Cool. All right. Well, thanks. And I guess we'll wrap up then, Jordan. Anything else to?
All right. We're all good.
All right.
Until next time.